Hi, in my latest video about this new Rigol MHO 980 series oscilloscope, in particular this model which goes up to 1 GHz, but the 984 for example goes up to 800 MHz, and you can software expand the base 350 MHz model right up to 800 MHz. It's just a software option. And thank you to one of my viewers, YAQ1988, for putting up this comment, which is rather interesting, saying basically what use is greater than a 350 megahertz scope, which is what the base model version of this introduces for like under $1,000 now. You can get a 350 megahertz scope. The question is, well, what's the point of having anything higher frequency than that, like the 500 megahertz model, the 800, or even the 1 gigahertz like this HMO 98 here? What's the point of that if the inputs here, they don't even have the times 10 ring around here to identify a times 10 probe, let alone an active probe interface to power a high frequency active probe? So what is the point of having a higher frequency scope like this if you can't plug any high frequency probes into it? Well, that's a good question. The answer is you actually can, and you can do it for like a couple of bucks. Now, I've actually done a video on this before, video number 1367, and that was actually a two-part video, but it was actually, the pertinent information here was actually buried away within that video. So I thought I'd extract that information out, and I'll include it at the end of this, but I'll just go over a brief summary. Now, this is the probe that comes with this new Rigol oscilloscope. It's a typical times 10 passive probe here, and it's a pretty high, decently high frequency jobby here. It's the RP3500A. It's a 10 meg input impedance, 500 megahertz bandwidth probe. And generally speaking, this is, like really high end for a passive probe. They do actually go higher though. So technically you could buy the 500 megahertz model. You've got a matching 500 megahertz bandwidth probe here. What's the problem? Well, there's a big problem. It's this number right here, 13 picofarads or 13 puff input capacitance. And as he mentioned in the comment, well, what about at high frequencies? That capacitance is going to matter. Yes, it is. You should be familiar with this formula. It's the capacitive reactance, XC, and it's 1 over 2 times pi times the frequency you're talking about times the capacitance, and this is frequencies in hertz, capacitance is in farad. And if you take this 13 picofarads here, you plug it into the formula at 500 megahertz, you get and capacitive reactance, or an impedance, or AC resistance, or AC impedance of, or basically a resistance and input resistance of your probe at the tip, right at the tip here. It's not 10 megohms anymore, it's 24.5 ohms. You've got to remember, this 10 meg only applies for DC. Anything over that, you have to apply the capacitive reactance formula due to the input tip capacitance of your probe here. So you might have your fancy-pantsy 500 megahertz oscilloscope and your fancy-pantsy 500 megahertz passive probe here matching, but if you try and measure a 500 megahertz signal or 500 megahertz component of the signal, at that frequency, you're really loading down your circuit under test. Like 25 ohms, that is ridiculously low loading there. That could definitely change your measurement. It could load down the line, it could cause your product to stop working or whatever. It's a really low value. You don't get the 10 megohms anymore. You don't get a free lunch with any probes. And you can get even higher bandwidth passive probes like this. This Roden-Schwarz jobby here, there you go, it's a 10 megohm, but it's 9.5 picofarads, and this is 700 megahertz. So not too shabby, but they're a little bit pricey. And here's one of the duck's guts of the passive probe world, the Tektronix TPP 1000. It's a 1 gig passive probe, standard times 10 passive probe. It's got 3.9 picofarads and 10 megohms DC input impedance. So this is really schmick. But a couple of downsides is it's not cheap, and B, it's like the customized tech interface. So even though it's not active, it still physically can't plug into a normal scope, which is really annoying. But anyway, there's others on the market. But it doesn't matter how good these standard passive probes get, you're still bothered by that pesky input capacitance. In this case, like 9.5 puff, almost 10 puff there. That's going to be a really low impedance. Run the numbers yourself. The general solution to this problem is, of course, these fancy-pantsy active probes here, and I've done videos on this, and this is a Keysight jobby, old school analog branding though, and once again, it's a 10-to-1 probe. Its input impedance though is 1 megohms at DC, not 10 megohms anymore, but that's neither here nor there. It's still massively high. It's a 2 gigahertz bandwidth probe, but it's only got an input tip capacitance of 1 picofarad, 1 puff there. So if you whack that into the equation here, at 1 gigahertz, 1 puff is 159 ohms. So it's still low, but it's not going to load down your circuit. That's way higher than the 13 picofarad passive probe up here. You've only got 1 picofarad now. It's 1/13th of the capacitance, but 159 ohms is still, it's still high-ish, but it's probably not going to load down a decently low impedance driving circuit that you typically measure with these things. But the problem with these active probes is usually they require a custom interface matched to the manufacturer's oscilloscopes. And if your oscilloscope doesn't support those, then you can't use an active probe. Or can you? Here's an Active FET probe, and active probe means that it actually has an active amplifier circuit right in the tip there, so you're minimizing your input capacitance. Go straight to the amplifier. This one actually plugs into a regular oscilloscope. This particular one's actually discontinued. You can't buy it anymore, but there are other brands on the market that will plug into a standard oscilloscope 50 ohm input. So you could use it with this new Rigol scope, for example. And this one here is 1.2 gig bandwidth, more than enough to match the scope at 10-to-1, and 1 megohm, 3 picofarads input capacitance. Not bad. And sure enough, Rigol do not actually sell an active probe to go with this oscilloscope. They do sell active probes, but they are designed to use the custom interfaces you get on the higher end at Rigol scopes. So you can't use them on this. But all is not lost. You can actually get a Rigol 1.5 gig passive probe called the RP6150, and it's 279 Yankee bucks. It's not that expensive. So you can actually get matching passive probes for your scope, and it uses a standard BNC 50 ohm input, which this scope is capable of. You don't need the active probe interface. You don't need any external power for this. This is a passive probe, and you can see that that probe has an input impedance of 500 ohms, so like across the entire frequency range. It doesn't really specify an input capacitance. It just says 500 ohms plus minus 10% across that 1.5 gig bandwidth. So that's pretty decent. How do they do it? That's the point of this video. And that brings me back to my previous video, number 1367. You can actually build your own do-it-yourself passive resistor probe, or a Z0 probe, or they go under various names. But, a resistive probe like this, it's simply a BNC with some coax and, in this particular case, a 1K resistor. Just a standard resistor, nothing fancy about it, right at the tip there. So the relatively high input capacitance of this cable is isolated by the 1K resistor here. So you get extremely low capacitance on the input. And you can build this thing yourself for a couple of bucks, and they perform just as good as that $279 Rigol probe, or even more expensive, fully characterized resistive probe. So what I'm going to do now is insert the video extracted from number 1367, explaining and demonstrating using one of these resistive probes here and how it compares with an active probe. A resistive probe, a Z0 or Z0 probe, and basically what it is a bit of coax, RG174 for those playing along at home, with terminating in a standard BNC, and in the end here, it's just got simply a 1K series resistor, and the braid just goes off here to your ground tip, and that's it, a 1K series resistor in a coax. How can this perform as good as like a multi-$1,000 probe even? Well, there's a bit of art and science to it. And they can basically match the, at least signal integrity performance of like a multi-$1,000, even $10,000 10 gigahertz probe, if you do these right. But yeah, there's a lot of art and science in getting it right. And this one here I just crudely made up. I haven't measured its performance. Once again, if you actually want to characterize the performance of it and know it's going to be good, then, well, you need all the gear and the experience to do that. But I have no doubt that even this simple one I just lashed together is probably as good in terms of signal fidelity as, you know, this 500 meg Agilent, not that Keysight rubbish, probe here. Okay, Dave, what's the catch? If anyone can just lash a probe like this together for practically zero cost, then why bother with like expensive high bandwidth probes like these ones? Well, the first thing is of course that gorgeous input impedance, that 10 meg ohms at DC. By the way, we'll get into that input impedance, and well, you know, it doesn't load down your circuit much at DC. But unfortunately, this puppy with a 1K resistor in series, these of course have to be terminated because this is a transmission line, and if you don't terminate the other end, you're going to get reflections galore, and it's just, well, it's not going to work as a probe. So you have to have a 50 ohm termination on your oscilloscope, either internal to the scope or just an inline one that you actually plug in. And if you run the numbers, put that into confuser, then with a 1K in series with a 50 ohm termination at the other end, you're talking about a 21 to 1 ratio, as opposed to a 10 to 1 probe. This is a 21 to 1 or 1 to 21. So it divides your signal by 21 times, and you've got a 1K DC impedance. So that loads your line down substantially. And of course, you don't need a 1K resistor in here in series. You can basically make it any value you want, make it larger or smaller, and you can have it. Of course, if you put in a 450 ohm resistor, then you'd have the same 10 to 1 probe as you would here. But the difference is, instead of having a 10 meg input impedance here, this one would have a 500 ohm input impedance, and that's going to load down your lines at DC. But the interesting thing is that this is 11 picofarads here, and at frequency, that is going to load down quite substantially. So now we actually have to talk about probe loading, whereas this is not going to have much capacitance at all. So hence why, in theory, you know, if you use the right coax and everything else, you can get, you know, 10 gig bandwidth or something, many gigahertz bandwidth out of these sorts of probes, if you construct them right and terminate them right, and all the rest. This probe with a 1K resistor in series, that's kind of like a typical value everyone uses. It's not too high, it's not too low, it's just right. It's like the Goldilocks value, and this probe is only going to have, like, you know, 1 or 2 puff, although I haven't measured this one, probably going to be better than this real expensive $800 probe here. So there has to be another downside to this, and yeah, there could be. If you choose like the 1K value in here, you've got that oddball 21 to 1 divider ratio instead of your more standard 10 to 1. So even a real, like, you know, highish end expensive scope like this Tektronix MDO 3000, 1 gig bandwidth up here, check out the probe attenuation. There, it's 1, 2, 5, 10. Well, we can get 20, we can get close, but we can't get that 21. So if you use that oddball value, then, well, you either have to just set it to 1 times 1 and then just do the calculations manually, or you can choose the resistor value to match. So you can get an E96 value resistor, like just over 950 ohms. That'll give you a reasonable, like, 20 to 1 ratio. But one other advantage of these is that they're actually slightly more tolerant of longer ground leads than a FET probe. So that's a benefit. So, you know, these things, if done right, are really very, very good. Okay, let's give you a probing example here. We've got a Raspberry Pi 3 for those playing along at home, and we're going to probe one of the memory pins on the bottom here. I don't care which one. I've just picked one at random. We're getting a signal on it. So I'm using the 2 gigahertz active probe here, the N2796 overkill for what we're doing. Well, overkill for this scope anyway, because this is a 500 megahertz bandwidth scope. So this active FET probe, more than good enough for measuring the bandwidth that we got here. So I'll use this long lead here for my ground. I'll put it on the ground pin of the connector there, because that's just very convenient. For those who care about such things, you can actually see what point I'm probing. Where is it? I think it's there. Geez, I can barely see that. This is where, you know, magnification comes in. Okay, I'm probing a point there. I don't know what it is. I don't care. There it is. There's our signal. It's made up of a whole bunch of stuff, but basically you can see, look, it's got some undershoot here. It's got a little bit of ring in there. It's got a little bit of ring in there. I'm going to hazard a guess that that's going to be due to our long ground lead there, right? Okay, so we'll just try and capture that sort of like the most frequent one there. There it is. Got it. Okay, so I'll store that. Right, so what I'm going to do now is I'm going to actually change the ground into this. Instead of having this longer lead, I'm going to go for one of the shorter little ground adapter pins we've got in there, and it looks like there's a little bypass cap. I've determined that this right hand side is the ground, so that's very convenient because that's right next to the point that I want to test. Otherwise, as I showed before, like you might have to like install one of those copper pads or something. You might have had to like scrape away some of the ground here or something like that, and maybe put the copper tape over the top of the chip or something like that, or you'd have to scrape away some other ground point somewhere, or you know, solder in a little contact loop pin or something like that. So here it is. I got my little adapter. Careful, because you can stab yourself with these little bastards. There we go. So we have this little now ground pin, which can sort of like, you know, pivot around like that. And anyway, that will make better contact, and this will be a higher frequency probe because it's a shorter inductive path. So let's try that. We'll require the tongue at the right angle and probably some magnification here. Okay, I've got my ground point and I've got my probe point. Pan up, pan up. Okay, let's have a look. I've changed my digitizer, definitely getting 5 gig samples per second, and I saved my reference waveform. So let's single shot capture that, see if we can get it. No. There we go, got it. Now I can actually adjust that waveform there to show you. There you go. So the orange one I've got there is the reference waveform, and this new yellow one is the one that we just probed. And there you go. It is like, it's of course like the same wave shape. You can see it's got the longer ground lead one. The orange one has some extra undershoot there and comes back and takes more time to come back up like that. And the one up here got some extra wiggle, 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 yeah, on the top there, some overshoot. So, you know, there are differences in probing right there. But at the moment, this is the loading of the line with a 1 picofarad, 1 puff active probe, which costs a couple of $1,000. Okay, now I'm going to use my 500 megahertz passive probe here. It's the N2843. It's 11 picofarads, okay? And yes, I've compensated this. You compensate it with your probe compensation on the front, so everything's hunky-dory. I'm using my low inductance, high frequency ground probe attachment, so that's equivalent to what we had before. So we should get, because we've only got a 500 bandwidth scope here, then the bandwidth of the probe isn't really going to matter that much. Hold my tongue at the right angle and probe this. I think I got it. But here's the interesting thing. I've changed the reference waveform to my low inductance short ground one before. So the orange one is the best we could get with our active probe. So the exact same ground point, basically the same ground length. And you can see that, well, you know, our wave shape's the same, but look at this. It's a much higher level down here. Okay, this is 200 millivolts per division, so it's like, you know, 50 odd millivolts higher there, and it's actually lower down here, our yellow waveform there. So, you know, although we can see like the wave shape and everything up here, it's like when the bus is loaded differently, because that's what this little, you know, ramp up here is going here. I don't know the architecture of the Raspberry Pi. It doesn't matter, but I know there's something happening there with there. And down here, we're actually seeing a larger drop across the bus here, which is interesting, isn't it? You know, there's significant differences here. This wasn't the exact example I wanted to show. I just, like, it's a random example, but you can see the difference here between a 500 meg passive probe and effectively, because of the bandwidth of the oscilloscope, a 500 meg active probe. They load down the circuit differently. And I know you want to see it. Okay, let's compare Dave's dodgy homemade resistive probe here with a 1K resistor in the tip. We'll give that a whirl. Got a 50 ohm terminate that, but scope can do that, no worries. Tongue at the right angle, tongue at the right angle. Fix that. Oh, Oh, check this out. This is absolutely fan-freaking-tastic. Now, what we've got here, the orange waveform, of course, is our reference Active FET waveform. That's a $2,500 Active FET probe. Yes, it is compensated because you do still have to compensate them, and it stores it internally because it knows the serial number of the probe, etc. And the yellow one is Dave's do-it-yourself couple of buck resistive probe. Look at this. What's going on here? Well, it's obvious that what's happening at this point right here is that the bus is actually going open or something. I don't know the exact architecture of what's, the pin I'm actually probing. It doesn't matter, right? It's like it's going open. And because the probe is 1 meg DC resistance, look at that. It's not going to discharge. Maybe if we got like a longer time period, it'd eventually do a similar, like eventually discharge or whatever. But you see that the bus has actively changed. But because we're now loading this bus down with a 1K resistor or a 1.05K resistor, because we've got the 50 ohm terminator as well, boom, this looks like, for all the world, and it is, an RC discharge curve. So there you go. What's that? 10 nanoseconds per division. I don't know. You can work that out, whatever, for those playing along at home. But you can see how the resistive probe actually completely changes the circuit that you're actually measuring. So sure, the signal integrity is excellent. Let's take a look at this, actually. If you have a look at the bottom here, you can see that both of them undershoot almost exactly the same. But you remember how I said that the resistive probe can actually be more tolerant of longer ground leads. I think they're both about the same length. I think they're practically near identical. Remember how I said it can be more tolerant on these than Active FET probes? This might be an example of this, because this is not, this is not some controlled experiment. This is just something I slapped together willy-nilly, and this is the result that we actually got. This is fascinating, right? They both undershoot exactly the same, but the Active FET probe, the orange one, actually, look, it overshoots again and it takes much longer to recover than the resistive probe. Look at that. So this could be an example of where this cheap-ass do-it-yourself resistive probe is actually outperforming this $2,500 Active FET probe in terms of signal integrity. But once again, this is not a completely controlled experiment, but this is what you can actually get. But of course, the limitation is that it loads it down much more, 1K as opposed to 1 meg, right? There's a huge difference there. And you might know, what's the difference between this load? Look, it's dropping with the 1K. Is that the effect of the 1K load over here? Well, it's actually not. If we actually measure that, because remember, it's a divide by 21 probe as opposed to the Active FET probe, which is divide by 10. So if we actually set up our cursors here and I've set them precisely to the same ground point here. Our resistive probe is, we're getting 55 millivolts there. So if you get your confuser out, 55 millivolts times 21, which is our probe, 1.155 volts. And this is it looks like it's a 1.2 volt bus. So it's it's maybe 50 millivolts under, but we have to measure the other one actually. So if we adjust that, we're talking about 60 millivolts there. So it's actually precisely 6 divisions there, and we were on 200 millivolts per division, so that's precisely 1.2 volts. So the resistive probe is actually measuring 50 millivolts less, and that could be the extra loading of the 1K load. You'd have to check out the driving strength of the driver actually used in this, which is the whatever ARM micros used on the Raspberry Pi or whatever. But because, as I said, we can't actually put in a actual ratio, it doesn't let us put in our own user-defined value. It only does these fixed ones. But if it did do that, then we could actually get, we've measured it. We can see that it's basically 50 millivolts under. So that could be like an extra 50 millivolts drop caused by the loading of the probe. That's what it seems to be the case. But once again, this isn't exactly a really proper setup controlled experiment. But that's possible, and it's kind of like, the sort of value that I'd expect. But you can definitely see the loading there. And by the way, no, this is not just a freak capture where know, the bus did something different than before. This happens every single time. No matter how many times I capture this, the 1K probe is definitely totally different to the Active FET probe here. And you can see, obviously, the bus was floating there, and then it went boom. No, I'm going to go actively low. And of course, the choice of resistor value is always going to be a trade-off. Like if you go higher and higher in resistance, then your divider ratio gets higher and higher and higher, and you can't measure low-level signals, and it's not that great. But the higher value in resistor you go, the more you can isolate the cable and system capacitance from the tip. So technically, the less you load in your circuit. But it's all a big trade-off. So there you go. I hope you found that useful. There's no shortage of either do-it-yourself or relatively cheap resistive probes, or even, active probes. Yeah, they're expensive, many thousands of dollars, although there's do-it-yourself active probe designs as well. There's a lot of open source ones as well, and they're just going to work just fine. So certainly don't worry about thinking that you're wasting your money buying a high bandwidth scope like this 1 gigahertz one, or the 800 megahertz model, or the 500 megahertz model, or whatever. No, there's lots of probing solutions available for your scope, even though it has no fancy-pantsy active input or even the ×10 input. Unfortunately, not all scopes have the ability to put in a customized resistive probe value. You choose your resistor value based on your requirements, and it might be 10 to 1, it might be 20 to 1, it might be some oddball value or something like that. But in this particular case, the RYGOL, if we go into the probe interface here, we can choose all these standard ones, fantastic, but in the case of my little custom one with a 1K probe here, this is actually a ×21 probe, so I can actually choose the user thing here, and I can do 21x, like that. Okay, bingo, I've got a ×21 probe calibrated for my little cheapy couple of dollar resistive probe here. Nice. So if you found that video useful, please give it a big thumbs up. As always, discuss down below. Catch you next time.